Okay, this is Cryptography, Math and Computer Science, Group 17, Math 789. We follow the book of Hofstein and two other co-authors. The first three chapters are available on Blackboard, and I will try to get chapters 4 and 5 uploaded there later in the week. The summer school course moves really fast, and I encourage you to keep up to date. I should also add that there will be help sessions on Zoom Monday to Thursday on class days at 7 p.m. So chapter 1 in Hofstein is an introduction to cryptography. It starts with the time of the Romans and even before, and the very simple codes that were used then. They were what are called substitution ciphers, where you simply have some rearrangement of the alphabet, and that's easy enough to read, and I'm not going to go over that now. What I want to concentrate on are codes that are used today, commercially and by governments and so forth. And the basic codes depend on some elementary number theory. And since number theory is not a prerequisite for this class, I am going to start with number theory. So what I want to cover today are sections 1.2 and 1.3. And 1.2 is on divisibility of integers. So standard notation is n is the set of natural numbers by which we mean the positive integers. Not zero. Zero is not positive. And this z is the set of integers, positive, negative, and zero. This is the basic definition. We have integers a and b. So a, b, in, this is mathematical symbols and epsilon for in. A, b in the set z, and b is not zero. So we say b divides a if there is an integer c such that a is b times c. So for example, 9 divides 36 because 36 is 9 times 4. 7 divides 1001. I hope this is true because 1001
Russ,
is
can you move
7.
the paper down a little bit?
Yep. 7 to 1.2. Sure that's right. 43. That's right. So this is the basic notion of divisibility, and some things aren't obvious when you just look at them, but as the book observes, 847 divides 485,331 because 485,331 is 847 times 540, 573. Don't do it by hand, because it'll take you a week and you'll still get it wrong. But a computer can do it in a microsecond. A common divisor of two numbers is the number that divides both of them. So a common divisor of integers A and B is a positive integer D such that D, so notation, D divides A, we write as D a vertical bar A. So D is a common divisor of integers A and B, if D divides A and D divides B. And the greatest common divisor, abbreviated GCD, of A and B is exactly the greatest common divisor of A and B. So I don't even need to write it down. So if I take A equal 12 and B equal 18, 2 is a common divisor. One is a common divisor. 3, 6, these are all common divisors. What's the greatest? These are the common divisors, and 6 is the greatest common divisor. And the notation that we use is GCD of 12 and 18 is 6. The GCD of 84 and 1001 is 7. And an important problem is how to compute the GCD of two numbers. And this was a method solved efficiently by Euclid more than 2,000 years ago. And this method to compute the GCD due to Euclid is at the basis of a lot of modern cryptography. So the first thing I'm going to do is show you the Euclidean algorithm to compute the greatest common divisor of two numbers. If you are a computer science student, or if you've taken a course in computing programming, it's likely that you already wrote a program to implement the Euclidean algorithm. If this were just a course for computer science students, I would have you do it, but this is a math and computer science class, so there's a limit to what I can expect you to do on a computer, but the more you can do, the better. And the key to the Euclidean algorithm is what you learn in elementary school, long division, or what is sometimes called the division algorithm. So if you want to divide 80,001 by 84. Let's see, this is what you should have learned in elementary school. 84 into 1001, this goes once, 84, 161. 84 goes into this just one time, I guess, 84. 11 take away 4 is 777. So 1001 has a quotient, when you divide by 84, has a quotient of 11 and a remainder of 77. So you can write 1001 is 84 times 11 plus 77. So you'll notice the remainder is smaller than what we're dividing by. And the division algorithm says that you can always do long division. and precisely the following. Suppose we have A and B positive integers. Then there exists a unique quotient Q and remainder R such that if you divide A by B, you get a quotient of Q and the remainder R, and the remainder is strictly smaller than what you're dividing by and greater than or equal to 0. So the division algorithm has two statements. Given positive integers A and B, you can write A as BQ plus R, with Q the quotient, and these are just the names, R the remainder, and the remainder is a non-negative integer, strictly smaller than what you're dividing by. And this is what you learned in school. Here's another example. This is in the text. Suppose we take A equal to 230 and B equal to 17. So I can divide 17 into 230. This goes once, 17, 60. 60 into 17 into 60 goes 3 times. And I get a remainder of 9. So 230 is 17 times 13 plus 9. This is my A, this is my B, this is my quotient, and this is my remainder. And I want to make one other observation. Suppose we want to find means compute, the greatest common divisor of A and B. So by the division algorithm, we can write A as BQ plus R, quotient and remainder, R is strictly less than B. If D is a common divisor of A and B, then let's see, D divides A, so I can write A as D times something, let's call it X. D divides B, so B is D times something, I'll call it Y. So if I write A equals BQ plus R, that's the same as saying that DX is B times Q dy times q plus b. B equals dx minus dyq, which is d times x minus y cubed. Oops, I'm sorry, r. So d divides a and d divides b. A is d times x, b is d times y. So let's look at r. What is r? R is a minus bq. So clean the way to write it. A is dx minus b dy times q. So r is d times, factoring out the d, x minus y cubed, which means d divides r. So if d divides a and d divides b, then d divides r. And conversely, if d divides r, then r is dz for some integer z. And if d divides b, so b is dy for some integer y, then a, which is bq plus r, is dyq plus dz, is d times yq plus z, which means d divides a. So if we look at this equation, take a, divide by b, you get a remainder of r. The common divisors of a and b are exactly the same as the common divisors of b and r. So the greatest common divisor of a and b is the same as the greatest common divisor of b and r. So this is a very important argument. And Euclid knew this, and this is the basis of what is called the Euclidean algorithm. So the Euclidean algorithm is basically a computer program to calculate the GCD, greatest common divisor, of two numbers a and b. And it's based on this observation. If you use the division algorithm, write a is bq plus r, the greatest common divisor of a and b is the same as the greatest common divisor of b and r. So maybe I'll follow the text and start with an example. Suppose we want to compute the greatest common divisor of 2024 and 748. So if I take 2024 and divide it by 748, you can check that 748 goes into 2024 two times and leaves a remainder of 528. So the greatest common divisor of 2024 and 748 will be the same as the greatest common divisor of 748 and 528, because this is the remainder when you divide 2024 by 748. But this is easier to calculate because the numbers are smaller. But now let's take 748 and divide by 528. 748 is 528. 748 is 528 times 1 plus 220. So the greatest common divisor of 748 and 528 is the same as the greatest common divisor of 748 and 220. Now if I take, greatest common divisor of 528 and 220. If I take 528 and divide it by 220, this goes into this twice. This is 440. So this is 68. No, 440 is 88. So the greatest common divisor of 528 and 220 is the same as the greatest common divisor of 220 and 88. And the greatest common divisor of 220 and 88, if I take 220 and divide by 88, this goes in 2 times. This is 176. So this leaves a remainder of 44. So this is the greatest common divisor of 88 and 44. If I take 88 and divide it by 44, this goes in twice with the remainder of 0. So the greatest common divisor of 88 and 44 is the same as the greatest common divisor of 44 and 0, which is just 44. It's 44 divides into 88, so the greatest common divisor of 44 and 88 is 44. So it took how many long divisions? 1, 2, 3, 4, 5. It took 5 long divisions to calculate that greatest common divisor. And of course, if you look at the remainders, every time you divide, you get a remainder smaller than what you're dividing by. And these remainders are getting smaller, the greater than or equal to 0, and a strictly decreasing sequence of non-negative integers must eventually get to 0 and stop. So that is a proof that this is a computer program, a computer algorithm that terminates.
So Professor, we can do this by hand by using the Euclidean algorithm, or you could like you said, you can make like a web program that can easily compute this.
Correct.
And for like our homework and stuff like that, let's say you prefer us to use the Euclidean algorithm to break down the numbers, right?
I prefer you solve the problem, whatever the problem is.
Okay.
How you solve it is up to you.
Professor, so hi. So you
Yeah.
said in the exam we're allowed to use a calculator?
Yes.
Okay, that's it. Thank you so much. Just want to double check again.
Yes. Okay. I mean, computers, calculators, abacus, anything is fine. Pencil and paper is also fine, but computers are generally a lot faster, as are calculators.
Okay, thank you.
So this is the Euclidean algorithm in practice. So one can formalize the Euclidean algorithm to compute the GCD of A and B. The first step isn't necessary, but it's optional if you like. We got R0 equal A and R1 equal B. So you take A and write it as BQ plus R, or then a better notation would be R0 is R1 times a quotient Q1 plus the remainder R2. And each step, you take your last remainder and divide it by the newest remainder. So R1 is R2 Q2 plus R3. Now, when you divide R0 by R1, your R1 is bigger than the remainder, R2, greater than or equal to 0 always. When you divide by R2, the remainder R3 is strictly smaller than R3. When you take R2 and divide by R3, you get a remainder R4, which is strictly smaller than R4. So these are non-negative numbers, strictly decreasing. Eventually, you must get, let's say, RT minus 2 is RT minus 1, QT minus 1 plus RT. And eventually, you must get a remainder of 0. This sequence of successive long divisions has to stop. And the GCD of R naught and R1, which is the GCD of A and B, it's the same as the GCD of R1, R2, R2, R3, RT minus 1, RT, but then RT divides RT minus 1. So the GCD of A and B is going to equal RT, that is the last positive remainder in this sequence of divisions. Right. So this is the Euclidean algorithm. And if you are interested in algorithms, it's not enough to know that an algorithm terminates after a finite number of steps. The finite number of steps might be so big that the sun will have burned out and the universe and the earth no longer exists. You want to know that you can actually solve the problem in a reasonable amount of time. And at first glance, it looks like the number of iterations of this algorithm, since you have a strictly decreasing sequence of integers, it might be that you start with dividing by R1, you go down at least by 1 each time. So maybe the division algorithm could take up to R1 iterations. So let's see, what was the example we looked at? When we wanted to find the greatest common divisor of 2024 and 748, this could have taken 748 steps. But we see, in fact, it only took 5 steps, which is a lot better. And in fact, the Euclidean algorithm is always better than the worst possible estimate. So in the Euclidean algorithm, the number of iterations of long division to compute the greatest common divisor of A and B is not B. It's actually much smaller. It's at most less than or equal to 2 times the log of B to base 2 plus 1. So it's not B, it's like log B to base 2. And I assume by the time you've gotten to a 400 level math class, you know what log to base 2 means. So I already proved the first step. I proved that the Euclidean algorithm terminates in a finite number of steps. Let's just check and see that this is an upper bound for the number of iterations. And this is based on the observation that these remainders don't just go down by 1 in each step. In one instance, it might go down by 1, but if it goes down by 1 in one step, in the next step, the remainder decreases by a lot more. And the observation is that if we're looking at these successive remainders, so this is the claim, and if you follow in the text, this is on page 14, that IR plus 2 is in fact smaller than a half of RI. So you can't have RI plus 1 and RI plus 2 very close together. When you do 2 iterations, you've reduced your remainder by at least a half. And the proof of this goes as follows. So I want to prove this claim. So let's see, suppose we have, well, let's say there are 2 cases. Case 1. In fact, IR plus 1, the I plus first remainder is less than or equal to a half RI, but then the next remainder, IR plus 2, is strictly smaller than the I plus first remainder. So this is sort of the trivial case. if the first remainder is at least half, is no more than half of its predecessor, then the next remainder is even smaller. So case 2 is the more interesting case. Suppose that Ri plus 1 is bigger than a half Ri. So let's look at the division algorithm. You take Ri, you divide it by IR plus 1. Now, if IR plus 1 is bigger than a half Ri, and it's less than Ri, Ri plus 1 will go into Ri just one time. And leaves a remainder IR plus 2. Right? Of course, 2 times Ri plus 1 will be bigger than Ri. So when you divide, so in this case, when you divide Ri by Ri plus 1, the quotient is 1, and this is the remainder. So Ri plus 2 is Ri minus Ri plus 1. And now you take no, sorry, we can just leave it at this. Ri plus 2 is Ri minus Ri plus 1. But Ri plus 1 is bigger than a half Ri. So if you take away, this is less than Ri minus a half Ri. You take away something smaller, you get something bigger, and Ri minus a half Ri is a half Ri. So Ri plus 2 is less than a half Ri, and that's the whole proof. So every time you iterate the Euclidean algorithm twice, your remainder has dropped by at least a half. So what does that say? That says that if I look at the 2k plus first remainder, that's less than a half the 2k minus 1 remainder, which is less than a half. So this is a half, and the 2k minus 1 remainder is less than a half the 2k minus 3 remainder, which is a fourth R2k minus 3, which is less than an eighth R2k minus 5, which is less than a 16th R2k minus 7. In general, let's see, R2k plus 1 is less than 1 over 2 to the I every time R2k plus 1 minus 2i, which is 1 over 2 to the I, R sub 2 k minus I plus 1. So in particular, if I let I equal k, R2k plus 1 is less than 1 over 2 to the k, R1, which is B. Which means that if 2 to the k is greater than or equal to b, then b over 2 to the k is less than or equal to 1, which means R2k plus 1 is equal to 0. So the number of steps in the Euclidean algorithm is at most 2k plus 1. So let me just repeat that again. So if b is less than or equal to 2 to the k, then the number of steps in the Euclidean algorithm is at most 2k plus 1. See, b less than or equal to 2 to the k means that the log of b to the base 2 is less than or equal to k. So if I take k to be log b to the base 2, so if I choose the smallest k, such that b is less than or equal to 2 to the k, let's just say this is 2 log b to the base 2 plus 1. That's close enough. So the point is, the Euclidean algorithm is efficient. The GCD of A and B is computed in, at most, 2 log b to the 2 base 2 plus 1 iterations. So if you're a computer science student and you're studying algorithms, which means trying to estimate how long it takes a computer program to run, this is the Euclidean algorithm. It's actually pretty good. Now, there's one more. So that's the first thing. That's the Euclidean algorithm. This is something, to say the least, you need to know. Oh, no. One more consequence of the Euclidean algorithm. See if we can get a nice example. From the Euclidean algorithm, computes, let's call it D, which is the greatest common divisor of A and B. And more than that, there exist integers U and V such that D is AU plus BV. We can write the greatest common divisor of A and B as an integral linear combination of U and V. And we can do that by working backwards from the Euclidean algorithm. So let's look at the example I had computed earlier. I wanted to compute the greatest common divisor of 2024 and 748, and this is what I got. The greatest common divisor is 44. Here's 44. Now, let's work backwards from 44. So the GCD of 2024 and 748 is 44. 44 is 220 minus 88 times 2. That's 220 minus, but 88 is 528 minus 220 times 2, right? 88 is 528 minus 220 times 2. So that times 2, I'm just plugging that in for 88. What is this? This is 220 plus 4 times 220. That's 220 times 5 minus 528 times 2. But 220 is 748 minus 528. So this is 748 minus 528 times 5 minus 528 times 2. This is 748 times 5 minus 5 times 528 minus 2 times 528. That's minus 528 times 7. But 528 is 2024 minus 748 times 2. So this is 748 times 5 minus 528. That's 2024 minus 748 times 2 times 7. I have 748 times 5, 748 times 14. That's 748 times 19 minus 2024 times 7. That's 44. So I've written the GCD 44 as a linear combination of 748 and 2024. If you like, I would write this as plus 2024 times minus 7. So this is an integral linear combination of the two numbers whose GCD I was trying to find.
Excuse me, Professor, does it matter when you put like U equals like 748 or like V equals 2024, does
Well,
it
no,
matter?
the U and the V are the 19 and the minus 7.
Oh,
The
okay.
A and the B, the A is 2024, the B is 748.
Okay. So the U is 19 and the V is -7. Does it matter in which like position it is? Like if like it's like -7 is in front, right?
It
And
doesn't
then
make any difference.
doesn't make any difference.
No,
Okay.
it's the same number.
Yeah, because even if you rearrange it, it'll still be the same greatest common. Okay. I just want to make sure.
Well, I mean, let me just see the notation that the text is using. AU plus BV. So this is like 2024 times minus 7 plus 748 times 19. I just rearranged the order. It's the same number. Right? This is AU BV.
Mhm.
Here is BV plus AU, but it's all the same thing.
Okay, thank you, Professor.
Okay, so that is the Euclidean algorithm. Let's see if there's anything else we do. Next is what is called modular arithmetic. So this is section 1.3. So we have an integer, positive integer, m. And we say that integers, a and b, are congruent modulo m. So this is what we're defining, congruent modulo m, if m divides a minus b. And the notation is a, 3 lines, is congruent to b mod m. So m is called the modulus. So for example, 32 is congruent to 17 mod 5, because 32 minus 17 is 15, which is 5 times 3. 5 divides 32 minus 17. So 32 is congruent to 17 mod 5. It's also true that 32 is congruent to 17 mod 3. That's also a true statement. 29 is congruent to minus 11 mod 5. Because 29 minus 11 is 40, is 5 times 8. So
Professor, the modulus is like, it could be multiplied, it could be like broken up and like multiplied to equal like a certain value. Is that what
I don't
that means?
understand what you mean by broken up. The modulus doesn't change. The modulus is the modulus. Here, the modulus is 5. Here, the modulus is 3.
So can you like explain exactly like the modulus? Because I haven't really seen this before, like
Okay.
in
Take
my
a
math.
number m.
Mhm.
Well, a congruent to b mod m simply means m divides a minus b. That's all
Okay.
it means. M divides a minus b.
Oh, okay, okay.
Okay. So I don't know. 23 divides 72. Well, 23 divides 69, which is 72 minus 3. So
Mhm.
72 is congruent to 3 mod 23. 23 divides the difference.
Okay. Starting to make more sense now.
11 is congruent to minus 101 mod 2. That just means the difference is an even number. That's all it means.
Okay, thank you, Professor.
And congruences are fundamental in mathematics, and they satisfy a lot of simple properties. So in the text, this is proposition 113. So m is a positive integer. if A1 is congruent to A2 mod M, and B1 is congruent to B2 mod M, then you can add the congruences. A1 plus B1 is congruent to A2 plus B2 mod M. And you can also subtract the congruences. A1 minus B1 is congruent to A2 minus B2 mod M. And you can multiply the congruences. A1 B1 is congruent to A2 B2 mod M. So let's prove this. If A1 is congruent to A2 mod M, that means A1 minus A2 is divisible by M. Let's say it's M times some number Q1. Or A1 is A2 plus M. I shouldn't call it Q. Let me just call it X. So A1 minus A2 is MX for some integer X. Or A1 is A2 plus MX. And if B1 is congruent to B2 mod M, that means B1 minus B2 is divisible by M. It's M times some integer Y. Or B1 is B2 plus MY. So if I take A1 plus B1, that's A2 plus MX plus B2 plus MY. That's A2 plus B2 plus MX plus MY, or M times X plus Y, which means A1 plus B1 minus A2 plus B2 is a multiple of M. So that proves this identity. And if I were to subtract them, it would be A2 plus MX minus B2 plus MY. If I rearrange that, that's just A2 minus B2 plus MX minus Y. So again, A1 minus B1 minus A2 minus B2 is divisible by M. And if I multiply A1 B1, that's A2 plus MX times B2 plus MX. When I multiply this through, I get A2 B2 plus A2 MX, or M A2X, plus MX B2 plus M X B2 plus M squared. This should be a Y. So A2 B2, A2 M Y, MX B2, M squared XY. But all of this is a multiple of Y. This is M times Z for some integer Z. So A1 B1 minus A2 B2 is divisible by M. So that proves these three properties. Of the congruences. And another very important property of congruences is the following. So A and B are integers. So A is an integer. AB is congruent to 1 mod M. If and only if the greatest common divisor of A and M equals 1. In other words, given A, there exists a B such that AB is congruent to 1 mod M, if and only if the greatest common divisor of A and M is equal to 1. And if so, B is called the multiplicative inverse of A modulo M. And why is this true? That you can find a B such that AB is congruent to 1 mod M if and only if the GCD of A and M is 1. So let's prove this. So if AB is congruent to 1 mod M, that means M divides AB minus 1, which means AB minus 1 is M times some number C, for some integer C, which means AB minus CM is equal to 1, which means any common divisor of A and M has to be a common divisor of 1. So the greatest common divisor of A and M is 1. So if this congruence holds, then for some B, then A and M have to be relatively prime. That's the proof in one direction. And what about the proof in the other direction? If the greatest common divisor of A and M is 1, that means that there exist integers, U and V, or I'll call them B and C, such that AB plus MC equals 1. If A and M are relatively prime, there's an integer linear combination of them that equals 1, which means AB minus 1 is M times minus C. So M divides AB minus 1, so AB is congruent to 1 mod M. And that's the proof of the converse statement. Now, so suppose we fix a modulus M, which is a positive integer. For every A, by the division algorithm, every A, integer A, if you divide A by M, A is M cubed plus R, where the remainder is between 0 and M minus 1. Divide A by M, you get a remainder which is a non-negative integer, strictly smaller than M. So A minus R equals MQ, which means A is congruent to R mod M. R is some integer between 0 and M minus 1. So every integer is congruent modulo M with some number between 0 and M minus 1. Now, if you take R and S, integers between 0 and M minus 1, and if R is congruent to S mod M, what does that mean? It means M divides R minus S. But R and S are integers somewhere between 0 and M minus 1. So the absolute value of R minus S, the greatest distance apart they can be, is M minus 1. So M divides R minus S. If R minus S is different from 0, it's smaller than M minus 1. That's impossible. So R minus S has to equal 0 or R equals S. So these M numbers, of course, there are M of them, M minus 1 positive integers and 0. They're pairwise not congruent mod M. So every integer A is congruent mod M to a unique integer in the set of numbers from 0, 1, 2, up to M minus 1. And we call this notation for this, it's written usually Z slash MZ. And we're going to make this into a ring. I'm going to define addition, subtraction, multiplication of these things. This is going to be called the ring of integers modulo M. And by saying this is a ring in algebra, this means I have a way to add and subtract and multiply them. So, and the algebraic operations are very simple. You just define it to be so we have Z mod MZ consists of these integers. So for example, Z mod 6Z would be the integers 0, 1, 2, 3, 4, and 5. Right? M is 6, M minus 1 is 5. It's these 6 numbers. And for A and B in Z mod MZ, we define A plus B to be equal to C in Z mod MZ if A plus B is congruent to C mod M. Every number is congruent to a unique integer in this set. So given any two numbers in this set, add them and see what it's congruent to mod M for a number in this set. And A times B equals D, Z mod MZ, if A, B is congruent to D mod M. So let's actually compute the addition and multiplication table. Suppose I take M equal to 5. So Z mod 5Z consists of the numbers 0, 1, 2, 3, and 4. What is the addition table? So 0 plus 0 is 0. 0 plus 1 is 1. 0 plus everything is the everything. So, and 1 plus 0, 2 plus 0, 3 plus 0, 4 plus 0. 1 plus 0 is 1. 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. 1 plus 4 is 5. But there's no 5 here. But mod 5, 5 is congruent to 0. So 1 plus 4 is 0. 2 plus 1 is 3. 2 plus 2 is 4. 2 plus 3 is 5, which is congruent to 0 mod 5. 2 plus 4 is 6, which is congruent to 1 mod 6. 3 plus 0, 3 plus 1. 3 plus 2 is 5, congruent to 0. 3 plus 3 is 6, congruent to 1. 3 plus 4 is 7, congruent to 2. 4 plus 0, 4. 4 plus 1 is 5, which is congruent to 0. 4 plus 2 is 6, which is 1. 4 plus 3 is 7, which is 2. 4 plus 4 is 8, which is congruent to 3 mod 5. So that's the addition table mod 5. What is the multiplication table? It's a 5 by 5 table, so we have to calculate 25 numbers, but 0 times anything is 0, so that's easy. And 1 times anything doesn't change the anything. So now we just have to fill in this part, which is 1. 2 times 2 is 4. 2 times 3 is 6, which is 1 mod 5. 2 times 4 is 8, which is 3 mod 5. 3 times 2 is 6, which is 1. 3 times 3 is 9, which is 4. 3 times 4 is 12, which is 2. 4 times 2 is 8, which is 3. 4 times 3 is 12, which is 2. 4 times 4 is 16, which is 1. So that's the multiplication table mod 5, which you can check. It's actually calculated in the book also. The multiplication table mod 5. Now recall we proved that given A, there exists B with AB congruent to 1 mod M, if and only if the greatest common divisor of A and M is 1. So that Z mod MZ star is a set of all A in Z mod MZ such that the GCD of A and M is 1. This is called the group of units of the ring Z mod MZ. These are precisely the numbers which are invertible. So for example, what's Z mod 24Z star? This is all the numbers from 0 to 23 that are relatively prime to 24. So you have 1, not 2, 3, or 4, 5, not 6, 7, not 8, 9, 10, 11, not 12, but 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. 1, 2, 3, 4, 5, 6, 7. So there are 8 numbers that are relatively prime to 24 and Z mod 24Z, and those are the units. If you look at Z mod 7Z, these are the numbers between 0 and 6, which are relatively prime to 7. And that's everything except 7. And there's an important function called the Euler phi function. Euler is spelled E-U-L-E-R. Phi of M is the number of elements in Z mod MZ star. So you can see that phi of 7 is 6. Phi of 24, 1, 2, 3, 4, 5, 6, 7, 8 is 8, and so on. Okay. Let me do just one more thing today. Which is, this is on page 24, section 1.3, which is called the fast powering algorithm. So in two crypto systems we're going to use, RSA and Diffie-Hellman. Crypto system. We have to compute large powers of a number G modulo a number N, which is really big. So we want to compute G to the power A mod N. So you're given G, you're given N, you're given A. You want to compute this. And of course, one way is just to take A, take G, G squared, G cubed, keep doing this. But if G is even not very big, trying to do the calculation like this will take longer than the lifetime of the universe. Take A equal 2 to the 1,000. It's just too big. So the idea is to use, we want to find a faster way. And the idea is to use the binary expansion of the exponent A to simplify this. So here's the example that the text starts with. So it's a good enough one for us. Suppose we want to compute 3 to the power 218 modulo 1,000. So step one, write the exponent in binary. Right? Binary means it's a sum of powers of 2. So let's see, what are the powers of 2? 1, 2, 4, 8, 16, 32, 64, 128, 256. 256 is too big, so let me do it by hand. 218 is 128 plus 90. So that's 128 plus 64 plus 26. That's 128 plus 64 plus 16 plus 10. That's 128 plus 64 plus 16 plus 8 plus 2. So this is equal to 2 plus 2 cubed plus 2 to the 4th plus 2 to the 6th plus 2 to the 7th. So this is the binary expansion of 218. So 3 to the power 218 is 3 to the power 2 plus 2 cubed plus 2 to the 4th plus 2 to the 6th plus 2 to the 7th, which is 3 squared, 3 times 2 cubed, 3 times 2 to the 4th, 3 times 2 to the 6th, 3 times 2 to the 7th. Now, of course, we still need to compute these. So this is congruent to what? Mod 1,000. Well, let's see. Let's compute the powers of 3 mod 1,000. So I'm going to make a little table. I and 3 to the I mod 1,000. So I only need to know the powers of 3 up to the 7th power. 0, 1, 2, 3, 4, 5, 6, 7. 3 to the 0 is 1. 3 to the first power is 3. This is all mod 1,000. 3 squared is 9. I'm sorry. I don't want 3 to the I want 3 to the 2 to the I. I'm taking 3 to powers of 2. Actually, we'll see this. This is actually pretty easy. So I want 3 to the power 2 to the I. So when I is 0, 2 to the 0 is 1. 3 to the first power is 3. When I is 1, this is 3 squared. 3 squared is 9. When I is 2, this is 3 to the 4th power. No, 3 to the 4th power. You just do 3, 9, 27, 81. What about I equal 3? When I is 3, 3 to the 2 cubed is 3 to the 2 squared squared. 3 to the 2 squared is 81 squared. When you square 81 modulo 1,000, you can just do that by hand, I guess, right? Let's see, 81, 81, 1, and this is 8, 1, 6, 1, 6, 7, 1. Oops. Is that right? Let's see. 81 times 81, 81, 8, oh, 8 eighths are 64, that's better. 1, 6, 5, 6, 6, 5, 6, 1. But mod 1,000, this is just 561. 3 to the 2 to the 4th is 3 to the 2 cubed squared. That's congruent mod 1,000 to 561 squared. And that's a relatively easy calculation. When you do that, you get 721. You're successively squaring each of these numbers and reducing it modulo 1,000. So if you check the table in the text, you see 561, 721, 841, 281, 961. So if I have 3 to the power 218, that's 3 squared. It's this times this times this times. 3 squared is 3 to the 2 to the first power is 9. Times 3 to the 2 cubed is 561. Times 3 times 2 to the 4th is 721. 3 times 2 to the 6th is 281. And 3 times 2 to the 7 is 961. Modulo 1,000. And when you do this calculation, you get 489 mod 1,000. And the point is that to try to calculate this to the 218th power by just multiplying by 3 over and over and over again would take too long. I just leave it at that. Too long. And this fast powering algorithm works with very high efficiency. Again, if you are a computer programmer, you may have written the computer program to do this, but it is very efficient. All right, maybe that's a good point at which to stop. We've covered basically sections 1.2 and 1.3. Keep in mind that in summer school, each day is like a week's work. So this would easily have been a week during the regular semester. And this is what it is in the summer. Any questions about this? There is really quite a bit to learn. So I encourage you to study the text very carefully. Sections 1.2 and 1.3, and to work on the homework problems. Some of which are due on Wednesday, others on Friday of this week. Okay.
Thank you, Professor. Professor, you're gonna be teaching tomorrow again, right? At 11.
Sorry?
Are you gonna be teaching tomorrow at 11?
Every day, Monday through Thursday.
Okay, perfect. Thank you.
Okay.
Thank you, Professor. And to submit the homework again, right? Let's say we had to scan our papers, right? And then upload it through Blackboard, right? To submit it?
Yes.
Okay.
Yeah.
All right, thank
Okay.
you, Professor.
Be well. See you tomorrow, perhaps.
See you tomorrow. Thank you, Professor. Have a good day.
Thank you. Bye-bye.